Well, in the last hour, we already we are talking about the what the coefficient, how to interpret this coefficient of logistic regression, right? Okay, I say that comparing to linear regression, which is very straightforward, right? The coefficient is the marginal effect of x to y, and it's incremental, right? Okay, so just add, if x1 increased by 1, you just add b1 to the estimation value of y, right? It's quite straightforward. But in logistic regression, because of there are some mathematical complications, right? Okay, so it's actually, you can still imply the marginal effect of x to the probability of y equal to 1, right? It's not directly to y, right? It's actually the marginal effect to the probability of y equal to 1, right? So that's the first thing that is different, right? The second thing is that because it's log-arc ratio, so you actually take you need to take an exponent, okay? You need to do an exponential transformation of b1, okay, to acquire the arc ratio, okay? It's not the first thing is you need to like do the exponential transformation, and second thing is that it is actually do not apply to probability directly, right? It is actually the arc ratio, okay? So so the thing is like the exponent of coefficient estimate the ratio of arc, right? Okay, that's so a little bit complicated, but still this is the way to, right, infer the marginal effect of predictive variable to the probability of y equal to 1, okay? So that is the thing, right? So you need to remember that you need to take exponential, and the effect are multiplied instead of adding to each other, right? Okay, so and it's the R ratio instead of increment of probability. You need to, there are a few things that you need to take care of, right? So but you take some basically you just remember this sentence, right? This statement, and that basically explain how to infer the marginal effect of predicting variable to the probability of y. Okay, that's the thing. Okay, and actually, from time to time, instead of knowing the arc ratio, we want to know the increment of probability, right? For example, if I smoke one pack of cigarette, how many percent the increase if the risk of like lung cancer would be increased by how many percent, right? That's usually what people expect to know. That if you told them that a pack of cigarette would increase your arc ratio by how many, right? It's sometimes it would be desirable to calculate the incremental probability, but that incremental probability is quite difficult to calculate. It's not just like take an exponential transformation of coefficient. It's not that easy. Okay, if you really want to know the incremental probability per increment of x, then you need to do it this way, right? First of all, you need to like you need to know the value of every predicting variable, okay, before you can calculate the increment, right? In addition to the coefficient, you also need to know the value of x, okay? And usually we will use the median or average of the x, right? Okay, so we make a data frame, right? And in this data frame, I put the median of x1 and x2 in this data frame, and I do a prediction, okay? So this prediction actually predict the probability of y equal to 1 when x1 and x2 equal to their median, right? Okay. There is one thing I haven't mentioned yet, right? When you do the prediction of logistic model, you actually need to give them the model, the data, and it must specify that type equal to response, okay? In order to get the predicted probability, okay? So now you specify x and do the prediction, so you know that this is the probability that when x1 and x2 equal to their median, right? So so we know that we know the R ratio, right? Because if we only want to know the R ratio, then we use the coefficient and transfer by exponential transformation. But now we are not satisfied by this R ratio. We want to know the increment probability, right? So the way that you do the marginal effect is that here you compare these two code. Here I plus 1 to the median of x1, okay? So here is x1, x2, right? And you do the predicted probabilities this way, right? And here is I minus 1, sorry, I plus 1 to the median of x1, right? And you do the prediction again, right? So as you can see that when x1 increased by 1, the probability would increase by from 0.178 to 0.190, right? Okay, so the marginal effect of x1 would be equal to 0.190 minus 0.178. Okay, so you can do this. If you really want to calculate the increment of probability, okay, you actually need to specify the value of x first, okay, and predict the probability, okay, and then you increment the value of x, right, by 1, and then you get a second probability, and you can like do a you see the difference between these two probability, and then you can see the marginal effect. You cannot, in another word, you cannot know the increment of probability by the coefficient itself. Okay, the coefficient only can infer the odds ratio. It cannot infer the increment of probability. If you want to calculate the increment of probability, if you want to estimate the marginal effect of x, right? You need to know all of the value of x and do the inference in this way, okay? So here is some practice, right? Here I just set the x value, x1 and x2 to their median, right? Sometimes you want to know that we can take a quantile of x1 and take a quantile of x2, so that you know their q1, q2, which is median, and q3, right? Okay, so here is a practice, right? I said when these two predicting variable equal to their first quantile, which means that when alpha space is equal to 7 and nat tortoise equal to 0, right? What is the probability of poor cat, right? You simply can reuse the code here, right? But right now you replace this one and this one by 7 and 0, right? Okay, and then you know the probability of poor cat, right? Now, in terms of odds ratio, what are the marginal effect of the predictor? This is easy, right? Because you simply do a exponential transformation, right, on the coefficient, then you know the odds ratio, right? So in terms of odds ratio, the marginal effect is easy to acquire, right? But if you want to know the probability of increment, then you need to use this method, right? You need to define the data frame, and then you need to fill in in this data frame you put in the ratio of put in the value of x, and you predict the probability, and then you increment, you do an increment on one of the predictors, and then you can calculate the marginal effect in terms of probability increment. Okay, and that increment will change. Okay, if you change the value of x, okay, the odds ratio would not change. It would always be the same. Okay, because the coefficient is the same, right? Okay, but the increment of probability would change when the value of x change. Okay, so this is the practice that I would leave for your homework assignment. Okay, got it? Okay, so as we say last week, the usefulness of linear equation is that you can invert the marginal effect of x to y, right? But in logistical equation, we are not talking about y, we are talking about the probability of y, okay? And that coefficient actually can invert the odds ratio of y equal to 1, okay? And if you want to calculate the increment of probability, right? Then you will have to know the value of x, all of the x first, okay? And do the increment by yourself, okay? And not change. If the x value change, the increment of probability will change, okay? So that's a few complications in interpreting the coefficient of logistic regression, okay? Nowadays, most of the paper, they will simply report the odds ratio, okay? So it's quite easy. You just take to acquire the odds ratio, you simply like do an exponential transformation of the coefficient. That's easy. Okay. So, but the problem is when you sometimes it's desirable to know the increment of probability, but it's not an easy thing to do. You need to like know every x. Okay. So I will leave this for your homework this week. Okay. Any problem? Okay. Okay, if no problem, then let's proceed we only have 30 minutes left, so we may not finish all of the material we want to cover this week, but don't worry, we will continue with the same thing, with the same example next week, okay? See, actually, you really need to like come into office. The punctuation is important, right? So every week I'll have to wait for like 10 minutes, 15 minutes before I can start the course. So actually to squeeze the time that we can use. And it makes me nervous. And when I get nervous, I kind of like cannot explain I start to I cannot express myself very well, right? Okay, so so if you have questions, just like raise your hand, okay? And as I say, that next week is very important. I really wish that you can like come to the classroom on time. Okay. Oh right. Oh sorry. So now we after examining the coefficient, now we want to discuss the model accuracy of logistic regression. Okay, so actually the model accuracy of logistic regression is like as I mentioned here, in this is linear regression and this is actually logistic regression. Okay, so the modeling and prediction code are very similar. Okay. There are some difference, but very similar, right? To build a model, you just make a function call, right? This is LM, this is QRM, right? And to examine the coefficient, you do a summary, and here's exactly the same summary, right? And to predict the estimate why you do the predict, right? And here are all the same. You just call the predict, right? Okay. So the difference is that you need to specify type equal to response, right? So so they are different, but they are quite similar. To do model, you make a function call. To do prediction, you do another function call, right? You don't really need to know the mathematics that I mentioned in the past 2 hours, but now if you just want to build model and do prediction, you know how to use this GRM function and remember to specify family. You need to how to use predict function and remember to specify the type. That's all, right? Okay, but the model accuracy metrics are very, very different when we are talking about probability. Okay, so in linear regression, as we mentioned, we use R square and RMSE, right? Okay, to measure the model accuracy. But for logistic regression, we will have a lot of different metrics, and this metric are kind of complicated. Okay, so if we talk about the accuracy metric of classification model, actually classification model is the probability model. They are the same, right? When we do classify on a binary variable, we actually are estimating the probability associated with every class, right? The probability associated with y equal to 1, with y equal to 0, right? So classification model is actually probability model, okay? They are basically the same, okay? So when we are doing this classification, which means that we have actual value and we only have two actual values, right? 0 and 1, isn't it? See, because it's binary, right? So we only have two outcome value, actual outcome value, okay? And if we in the traditionally, when we do the prediction, we will treat every point that has a probability higher than 0.5. We will predict positive, okay? For those points that has the predicted probability lower than 0.5, we will predict negative, okay? So for every point, right, given x, you will have a predict probability, and when that predict probability is higher than 0.5, we will predict positive, otherwise predict negative, right? So every data point in our data set, okay, for every point in our data set, they will go to one of these four conditions, right? Condition number one, we call true negative, is that actually its actual value is 0, and we predict negative, right? And that is what we mean by true negative, okay? Because we predict negative and it is actually at negative, so we call it true negative, okay? The same is here. This is true positive. When it actually is 1 and we predict positive, okay? So it's called true positive, okay? It's so in this matrix, here and here, our prediction is correct, okay? But prediction is not always correct, right? Sometimes the actual value is 0, and we predict it as positive, right? In that case, we call it false positive, because we predict positive, but it's not, right? It's negative, okay? And the same is that for false negative, right? Okay. And this matrix, okay, this metric is called the confusion matrix, okay? Has a name called confusion metric, okay? If you go to Wikipedia, there is a term called confusion metric, right? And turn down, as you can see that here. This is the confusion actually is actually quite simple, right? It's only have 4 cells, right? And here is the actual, and here is the predict, okay? Okay. So now, so you have TP, TP, TN, FP, FN. You only have this 4 value, okay? So this is quite easy, right? Any question? Okay. So this is the way to calculate the confusion metric is the basic that we calculate the accuracy of, when we concern the accuracy of a classified model. So now, out of this Tn, Tp, Fn, and Fp, okay, we actually can define a series of accuracy metric. Okay, the first one is accuracy. Okay, accuracy, right? It's as you can see that it put all of these four number, it add them all together as the denominator, right? Okay, and the denominator is Tn and Tp, right? Okay, so this is the accuracy, which is the ratio that we predicted right. Okay, so it's called accuracy, isn't it? Right? You get the point? Because the denominators, all of the data point, right? And the number here and the number here, you add them together is the number that we predicted right, right? So it's called accuracy, okay? Now, the second thing that we used to use is called sensibility. It's also called true positive ratio. Okay, as you can see that the denominator is Fn plus Tp, so it's actually this row, right? Okay, so it and its denominator is the positive, right? So it implies that given the actual value is 1, okay, the ratio that we can detect it as positive, okay, which means that out of all of the this actually 1 case, the model can predict it as positive, the ratio that we predict as positive. So it's called sensibility, right? For example, like sometimes sensibility is very important. For example, like the COVID-19 testing, right? If someone is positive, you don't want to miss it, right? Okay, so if someone is really is actually 1, and you want to have a high sensibility, right, to detect it. Okay, so it's sensibility is kind of like given it's actually 1, the ratio that we can like predict it as positive. Okay, that is called sensibility. Okay, and then the other metrics, the other accuracy metric is called specificity, and it's kind of like a reverse of sensibility. As you can see that the denominator is Tn plus Fp, right? So it's this row, which means that given that a subject is actually 0, the percentage that we can specify is negative. Okay? Okay. So in this case, that you want to be specific, right? When it is 0, I want to be very specifically detect the 0, right? So the sensibility and specificity respectively indicate the ratio that we can detect positive case and negative case. Okay, so accuracy is kind of like the total, right? So it's the denominators, all of the data point, and the denominators actually the number that we predicted right. Okay, so if you go to that Wikipedia page, you can see that out of this, actually the confusion manager only have 4 numbers, right? But out of this 4 number, they actually can define a lot of things, right? As we can see here, that we can define the, where is sensibility? Let me see. This is the confusion metric itself. And all of these are the things that we can predict. For example, here is sensibility. And sensibility is also called recall. It's also called true positive rate, right? And we can define false negative rate. We can define positive likelihood ratio. Out of all these 4 numbers, we can define a lot of things, right? Okay, but in this course, we only I think in this course we only take care of accuracy, sensibility, and specificity. That's it now. Okay. Of course, when you read the literature, you might read some. For example, you read like recall, right? And when that happens, you go to the wiki page, and you can see that whatever it is always derived from these 4 numbers. Okay, it's just like the way, the reason that there are so many accuracy metrics in probability model is that it is very useful, right? And every different discipline has their own way to to define the accuracy metric. Okay, but when we are doing decision, we will always go back to the basics, which means that we will always go back to this 4 number in the confusion metric, as I will specify later. Okay. So as I say that when we do the prediction, usually, I should say traditionally, we set the threshold probability at 0.5. Whenever the predicted probability is larger than 5, we would say positive. 0.5, we would say positive, and so the threshold is at 0.5. But actually, in practice, the threshold can be adjusted. Okay, in the modern way of business analytics, sometimes it would be very desirable to change the threshold, right? Okay, and when you change the threshold, the total value inside this matrix is always the same, right? But when you change the threshold, the number within the cell, the numbers within the cells will change. Okay. For example, if I change the threshold from 0.5 to 0.8, okay, the larger the threshold is, the less positive case it is, right? Because the way that we distinguish positive and negative is that above the threshold, we will predict positive, right? So if I set the threshold here, right, I mean that above the threshold, we will predict positive. Below the threshold, we will predict negative, okay? So when I raise the threshold to 0.8, how many positive cases do we have? You can tell the number here, right? Isn't it? Right? We only have 3 points would be specified as positive, right? And 1 point is false positive, and 2 point is true positive, right? Okay. And here actually I and make a plot. I call it distribution of predict probability. Okay, so here I actually because for every point in our data set, okay, for every point in our data set we have a predicted probability, right? So first of all, I actually take all of the data point that actually y equal to 1, and I draw it in, I draw the histogram in red color, okay? And for those points that y equal to 0, I draw their predicted probability, the distribution of their predicted probability in green, okay? So this is the distribution of predicted probability, and the red one is for y equal to 1, okay? And the green one is for y actually equal to 0, okay? So in this way, we can count, right? We can count, right? If I set the threshold to 0.8, only 3 points will be classified by the model as positive, okay? And out of these 3 points, 2 points is actually, they are red, right? So these 2 points we predicted right, and this point we predicted wrong, isn't it? Okay? So when the threshold can be adjusted, the higher the threshold, the less the positive case, and the more the negative case, right? Because the total case is usually the same, right? And when we move the threshold, actually the total number will not change, but the value inside the cell will change. Okay? And if the number change, then when the number change, because that all of this accuracy metric are tied to this number within the cells, right? Okay. So when the threshold change, the accuracy metric also changed. Okay? So traditionally, I mean that when we define this metric, we set the threshold at 0.5, but in the for practical reason, I will explain next week that sometimes it's desirable to change the threshold. Okay? For example, like in the poor cares, you might want to apply some predictive prevention medication care, right? To those who the probability of poor care is higher than 80%, right? Okay? It's not necessarily that you want to take action for like 0.5, right? Sometimes you want to take action on lower probability, okay? In that case, you lower the threshold and the number of positive will raise, okay? And sometimes you want to like do the prevention on less people, then you can raise the threshold, right? And that in that case, the number of positive will reduce, okay? So when this threshold change, the accuracy metrics will change with it, okay? So here I'm giving you a simulator so you can see it better. Here is the ENDPPSIM.R, right? You open this file, and this is actually an app. So you press this run app. You should see something like this, right? Usually I will open it in browser to be easier to see. Okay, so here is the as I see it, this is the classify the predictive probability distribution, right? So here this is the simulator, right? So I can actually change the it's simulated, it's not real, right? But I can change the mean and the standard error of this actual y equal to 0 and actual y equal to 1, right? Okay. This is the actual value of y, but our model would actually predict the probability, right, for each point, right? So there will be a distribution of this y, okay? So as you can see that here is if I set the threshold to, for example, if we have a model like this one, and I set the, after I do the prediction, I have the predicted probability of every point, right? For 1 and also for 0, right? Okay? So above this threshold, I will always, I will predict positive, and below this threshold, I will predict negative, right? Okay? So this is the TN, FN, TP, FP. This is the confusion metric, right? And these are the accuracy metric that derived from this 4 value, okay? But one thing that you can see, let's see what's the time. Actually, we are running out of time. The thing that I can cover here is like, if I raise the here, because it's simulator, right? So I can actually raise the threshold, okay? If I raise the threshold, okay, you can see that the sensibility is getting, if I put the threshold higher and higher, the sensibility would reduce, right? Okay, to the optimum, if I set the threshold to 1, okay, if I set the threshold to 1, then every point will be predicted as 0, right? Isn't it? Right? So I have no chance to detect any so the sensibility will be equal to 0, right? But in the other way, the specificity will be equal to 1, right? Isn't it? Because if I set that threshold to 1, then every point would be predicted as negative, right? Isn't it? Right? So given that you are negative, I will always catch you, right? But if you are positive, then I will always lose you. So my sensibility would, oh, okay. And in the other extreme, if I set it to 0, what happened then? Now sensibility will be equal to 1. Because above the threshold, I will predict 1, right? So every point is predicted as 1, right? So every 1 would be detected, would be captured, right? So, but there's the price. If I set the set it to 1, then the specificity will reduce to like 0, right? That would be the price, right? So as you can see that usually when you change this ratio, there is a trade-off between sensibility and specificity. Okay, the more sensitive, if I the smaller the threshold, the higher the sensibility, right? But the lower the specificity. Okay, and if I raise the threshold, the higher the threshold, the lower the sensibility, the higher the specificity. Okay. Here comes the question. So for every specific business context, okay, sometimes you want to emphasize specificity, sometimes you want to emphasize sensibility. Okay, and for every model, right, this is kind of like the model outcome, right? If you change the threshold from 0 to 1, you can actually draw a curve. Okay, they will actually can draw a curve in the space of sensibility and specificity. Okay, and the area under this curve is called AUC, is area under curve. Okay, as you can see that this AUC will not change. Okay, because this AUC is already considered all of the threshold, right? Because it is the kind of like the trace. Okay, when we change the threshold from 0 to 1, right? Okay, so this curve is called ROC curve. Okay, this is not Republic of China. This is a coincidence. Okay, so this ROC curve is actually the curve that when we change the threshold from 0 to 1, the point, all of the you have a curve, and the area under curve is called the accuracy. It's called AUC, is area under curve. Okay, and it has a very, very important. This curve has a very important implication in the real application. It actually would it actually would equal to the ratio that the model can correctly distinguish the two type of data points. Okay, if you have a very, very good model, right? So let's go back here. If you have a very, very good model, if you have a very good model, maybe if you can make a model like this. Okay, so you basically predict every one, the predicted probability is higher than 0.5, right? Okay, and for every point, you can see that the AUC would be equal to 1. Okay, if your model is so good that you can predict every one, the predicted probability is higher than threshold, and this one is lower than threshold, then you will have all metrics equal to 1, right? But this is not realistic. Okay, in realistic, it would be more like even more like right, even more like this, right? In realistic, you will see a ROC like this one, okay, and you will see a trade-off between sensibility and specificity. It means that the classified distribution of probability, they would overlay, okay, but when they are not overlaid, when they can when they are not overlaid, okay? When they are not overlaid, you will see that the model can distinguish the two class completely, right? So that the AUC would equal to 1, okay? So actually, I told you that this AUC has a very, very important implication, right? It indicates that when I randomly select 1 point for each of the two class, the ratio that the model can correctly discerning the two, okay? So it means the ratio that the model can distinguish the two class, okay? So, and it actually concerns all of the, it already calculate all of the threshold values, right? Okay, so it's not, it is not like accuracy, sensibility, and specificity, which would change when threshold change, okay? This AUC would not change, okay? With threshold, because it already consider all of the threshold in that, okay? So in modern business analytics, we would prefer to use this AUC as our accuracy metrics, okay? And now we are already running out of time, okay? So I think that's all I can do today, okay? We have some, so we will continue next week, okay? Because we do not finish Notebook C yet, okay? So this week's personal assignment is just to do A and B, right? Okay? So we will continue on Notebook C next week. And most importantly, we want to know that on the basic of prediction, how can we do the actions? Okay? So next week, I told you that it's the most important week of the entire semester, because doing prediction is not our purpose, right? Our purpose is to determine our strategy, to design our strategy, right? To make decision according to the prediction, right? Okay, so, and that pretty much concern the confusion matrix and also the classified distribution of predicted probability and also the threshold. Okay, so, because after all, you want to determine about which threshold I want to take action, right? That is the key question, right? And we will try to do that in next week, okay? All right, so that's all for today. Is there any question? It's already 8 AF to 12. So that's all for today. I will see you next week. And try to be punctual, right? Don't delay the class.